Okay, hi again, this is part B. Follow up with part A if you haven't already. So they are asking now part C. This is part 2 of the video, but we have reached part C in the question. What is the probability of having the two messages identical and erroneous and an erroneous intersection? So, well, identical, we actually know how they can be identical. Each bit actually should follow this thing. But what is the meaning of being erroneous? Being erroneous means that the 00 wasn't received as 00, it was actually received as 11. Or the 11 wasn't received as 11, it was received as 00. So actually, as if they are insisting, when we discussed in the early video these cases, as if they are insisting that it must be flipped. The two bits must be flipped. So they are not interested in this case. They do not want this case, and they do not want this case. They want this case to be at least in one bit. At least in one bit might be in one. The first bit might be the second, might be in the first and the second, might be in the first and the third, might be in the nth and the n minus one, but might be in 3 bits among the n bits. But they must be. So. So here the answer would be k starting from 1, because k starting, this is the answer actually. K starting from 1 means that k starting from, actually it is the same answer. No, I'm sorry, it is like from 0 to n minus 1. It is from 0 to n minus 1, okay? From 0 to n minus 1, because here for when we reach the n, so this nothing will become flipped, and this is not what we want. We want at least something to be flipped, so it must be it must be. So this is the thing, okay, which is fairly easy. This is the answer to the part C. But another answer actually I came up with, and actually it was my first answer, and I want to show you that my trial. Okay. Listen to what I made actually. This is what we want: probability of the two messages being identical, and I'm sorry. So let me show you this like this, like this, like this, like this. The probability of the two messages being identical and erroneous, there is an error. So this is a probability of identical, which is why did I think this way? Because we have already calculated this in the part B, times, we are talking about the whole message, okay, the whole message. We are talking about the whole message being identical, and not just only one bit. Actually, these two are identical. Yeah, identical, okay? So times probability of having an error, which means that something has to be flipped. Knowing that it is identical, knowing that the two messages are identical. Now, yeah, I actually okay, a probability of having an error maybe in 1 bit, in 2 bit, in 3 bits, but knowing that it is identical. Actually, this is not so so obvious to calculate or but it is easier to apply a certain formula, because here I don't know, at least for me, at least for myself, I found it that it is easier to work with the intersection rather than the knowing that. the conditional probability. And this is what I thought of. This is okay. We don't have a problem. The probability of error being identical is 1 minus probability of correct and being identical. Why did I go this way? Because correct is only it is all must be not flip, not flip, not flip. It's like you are studying only one case, which is something like that. But nevertheless, this thing is not easy to compute alone. I mean, knowing that it is identical, it is like you are saying that I know that if I know somehow the observer, the receiver, he knows that these two are the same, and he wants to know if it is correct or not. I really found this not to be so obvious to calculate or to deal with. So what I used actually, I used this as 1 minus probability correct. Yeah, 1 minus probability correct being identical, and 1 minus now probability correct of all the bits being correct, knowing that the two messages are identical, is actually all the bits are correct and identical, which is easier to compute, over probability of the two messages identical. This is easy. We know this. This thing is the same as this thing. Now, what is the probability of being correct, knowing that it is identical? It is actually being correct, so all not flipped, and they are identical. It is 1 minus p squared, all of it to the power n. It is 1 minus p squared, all of it to the power n, because we already discussed this, but I'm saying it again. So probability of not being flipped, which is this thing and this thing, and both the if we add these two together, it will become 1 minus p squared. This is only for one bit. Now having it for the n bit, so it is 1 minus p squared times 1 minus p squared times 1 minus p squared n times. So it will become 1 minus p squared all to the power n, because all they are independent. So with a little of putting everything together, probability, this is what we want, erroneous and identical. It is, if we put all these together, this and this, we obtain this thing. It is this thing minus 1 minus p squared and all to the power n, or same as saying 1 minus p to the power 2 times n. And this is the answer. And this is the, now the numerical application, you can do it alone. Now I hope all this can help. Take care, and if you have any question, you can put it. I really didn't want to. I disabled the comments on YouTube because they want. So I don't know. I don't know your age, so I put the video as made for kids. I know you are not kids, but I made it this way because legally they consider a kid to be like below 18, or I don't know. But I really consider that you are adults. If you have a comment, I don't know, you can put it on Facebook or somewhere else. Take care, and if you have a question, do ask. And it was a good experience to me.